Hi, everybody. How's it going? Welcome to Project Tier's speaker series presentation with Daniel Lakens. My name's Chris Conway. I'm a faculty in psychology at Fordham University in New York City, and I'm a fellow at Project Tier, whose primary mission is to improve the way that we teach undergraduates and others about transparency and reproducibility in scientific research. So today's talk is actually part of 9 talk series that are all on the open science movement, and it's been sponsored by the Sloan Foundation. And so this talk and the other ones in the series are going to be posted on Project Tier's website later on. So now onto the good part. It's a pleasure to introduce Daniel, who's an experimental psychologist at the Eindhoven University of Technology. And he studies, among other things, research design, applied statistics, meta-analysis, and meta-science. And he's earned plenty of awards for his teaching, and you can see why if you check out his free course through Coursera, which is called Improving Statistical Inferences. It covers frequentist and Bayesian approaches, power, effect size, philosophy of science. It seems to me to be equally helpful for beginners and more experienced researchers. He also has a blog called The 20% Statistician, where he reviews recent work, previews his own ideas, and he makes available R packages that he's created and other software tools for researchers. I could go on. He is a very important figure in the open science community, and I think we're lucky to hear his talk today on falsifying predictions in practice. Don't forget to post your comments and questions for Daniel throughout. Using the chat function. I think it's called the Q&A function, and you can see it if you hover over the Zoom window. So I'll pose your questions to Daniel as time permits at the end of his talk. And now I'm gonna turn it over to Daniel.
All right. Hi, everyone. It's a pleasure to be able to talk to you. I'm going to talk about a topic that is something that we typically don't try to do, namely proving ourselves wrong, making sure that if we do something that's not correct, if we make predictions that are not correct, that we can actually show that we proved ourselves wrong in something, which we do by trying to falsify our predictions. Now, if we think about how we do research, then one of the problems that we have in science is that people very often calculate p-values if they do statistical tests. So they collected some data and then they analyze it and then they compute some p-values. Now, I have to say that I'm one of the maybe 3 people left alive who don't think p-values are the biggest problem that we have. If you use them wisely, it's sort of okay. Regrettably, we don't really use them wisely. We already know this. So we use them as a threshold to decide what to publish. And they were never intended to do this, but people do this nevertheless. As a consequence, we see that mixed results and non-significant results are less likely to end up in the scientific literature. And this is a problem, right? Sometimes we just turn out to be wrong about something. And we should be able to share these results in a useful way so that other people can learn from them. We know from meta-scientific research that this is not the case. So if we take a look at this study by Franco and colleagues, and they published this in Science in 2014, what they did is they looked at what people did with the study results they got from a very large study project where people can submit study ideas. And if they are accepted, they collect a huge representative sample for their study. So this is a super useful service. It's called the time-sharing experiments in the social sciences. And these people will get a representative sample of whatever they want to study. So what Franco and colleagues did is they looked up these people after a while and they asked, so what did you do with the results that you got? Did you not even write them up, and do they remain unpublished? Do they remain unpublished, but have you written them up, and are they maybe undergoing the peer review process, or have they been published? And they looked at this as a function of whether people found null results, so no significant results, mixed results, or very strong results. And if you look at the table, you see that for strong results, most of these findings have been published. Some are still undergoing the peer review process. They've been written up but unpublished, and only 4 of them are not written up. The story is completely different for null results in the top row. There we see that Only 10 of these studies have been published. The large majority has not even been written up. So this is, of course, problematic. We don't really want this to happen. And if we take a step back and we think, what should we find if we do sets of studies, then, well, you can sort of think about doing a set of maybe 4 studies. What should you find? Should everything be statistically significant? Turns out that that's not the case. So let's say that you're planning to do maybe 4 studies in a paper. I mean, I'm an experimental social psychologist, so this is possible. Sometimes we do 4 studies and we report them in a single paper. Or maybe you're doing a PhD where you would do 4 studies in total. Let's say that you manage to have a statistical power for each of these studies, and statistical power is the probability of finding a significant result if there is a real effect to be found. So let's say that you manage by increasing your sample size to get the statistical power up to about 80% for each of these 4 studies. What's then the probability that you will only find significant results? Well, that's the probability of finding a significant result in study 1, which is 80%, multiplied by finding a significant result in study 2, and in study 3, and in study 4. So altogether, over 4 studies, about 41% of sets of 4 study papers should have only statistically significant results. Now, if you open a scientific journal, that's not what you'll see. You'll see that people mainly publish only sets of significant results, and these non-significant results are missing. What's also the case is that these people never seem to be wrong. Everything they do matches their predictions perfectly, which is a small miracle. So we have a peculiar situation where scientific journals don't really represent reality because it's not possible that everything works out. So what's the problem here? Well, first of all, a big issue is that this is actually not very ethical, according to some people, and I tend to agree. So this is a quote by Greenwald from a paper from 1975, and he says, first, it is a truly gross ethical violation for a researcher to suppress reporting of difficult to explain or embarrassing data, such as null results, in order to present a neat and attractive package to a journal editor. So you're not supposed to leave out these non-significant results and only publish everything that works. Indeed, if we look at the Code of Research Integrity, these sentences are from the Dutch Code of Research Integrity, but you'll probably have a similar one wherever you're working. We see that there's this point, do justice to all research results obtained. So it's pretty clear. You have to do justice to everything you find, whether it's a significant result or a non-significant result. So that we don't do this is a real problem when we're trying to interpret the evidence in the scientific literature. Now let's first ask a question. So if you are doing research, if you are doing a study, if you're a scientist, let's ask a question. Have you ever actually designed a study with the goal to show that there was no effect? So did you design a study with the explicit goal to show, look, this group of people will score exactly the same as this group of people? I think it's quite unlikely. For some reason, most scientific research questions that we study have the goal to demonstrate that there's a difference between 2 groups or some effect is happening. We never predict that the difference will be 0. We always think that there's some difference between these groups. This is interesting, and I think in part, the reason that we do this is because we actually don't educate people how to statistically falsify their predictions. We teach people null hypothesis significance testing, which is a very useful technique, but limited, because the only thing it allows you to do is to reject the null. So if this is the only tool that you've been taught, then of course, the only thing that you can do in your scientific papers is reject the null. So you can never really falsify your predictions. You will always be able to reject the null, so predict some effect, but you'll never really be able to falsify your predictions. You need to be taught a different statistical technique for this. And luckily, in recent years, people have proposed a couple of methods to actually do this, and I'll mention these at the end. So if at this moment you're like, I don't really know what to do, don't worry, before this hour is over, you will have some idea of where to start. So sometimes we want to demonstrate that there is no difference between groups. So we want to demonstrate the absence of an effect. It might be interesting for different reasons. For example, now I'm talking to you over a webcam, over the internet. And we hope that this is, of course, an efficient way to communicate information. It might be that it is just as efficient as if I would travel all the way over to you and stand in a lecture hall and do this live in front of you. If the effect would be exactly the same, you learn just as much from watching this video as when I'm in the room, well, that would be very efficient. We can both just stay at home. Now in these times with the coronavirus, it's probably a very safe thing to do. It's also good for the environment. I don't have to take a plane and travel to wherever you are. So if we were able to show that some sort of intervention, a new intervention, so we teach people either remotely through the internet or we do it old school live in front of them, if these things are equally effective, that would be super useful to know. Sometimes we also have theories that predict that there is no difference or nothing should happen. And if your theory predicts this, it would also be nice if you're able to show that there's no effect that happens. So take a moment if you've designed research, or maybe if you have some study that you're building on, take a moment to think what would falsify the hypothesis in maybe the last study you've done or the next study you'll do, or in a paper that you read and that you really like. Take a moment to think, what would we need to do to be able to conclude that whatever they predicted didn't hold up, so that it was falsified. So if you think about this, the first thing that might come to mind is say, I think that the prediction would be falsified if we find a p-value that is larger than the alpha level. Because typically we conclude that the prediction was supported if we find a p-value that's smaller than the alpha level. So maybe you say, okay, if the p-value is larger than the alpha level, that means that there's nothing going on. Regrettably, this is actually a very common misinterpretation of p-values. It's referred to as the fact that absence of evidence is not evidence of absence. So if you don't find support for something, it doesn't mean that there is no support. Can maybe make this a bit more clear if we look at a picture here, which represents a null distribution on the left. So there you see the gray distribution centered at 0. So that's sort of the effects that we can expect if the null hypothesis is true. There's no real difference between two conditions that we're studying. The only reason we would find a statistically significant effect in this case, if the null is true, is when we find a type 1 error. And then we would need to observe a mean difference that's large enough to fall into the red areas on the left or the right. But this is under the null model. Let's take a look and think what would happen if there is a real effect. Which kind of effects would I expect to find then? So that's the black curve here. And the black curve represents a true effect, a mean difference of about 0.5. So if there is a true effect of 0.5, we would find effects, well, sometimes 0.5, but sometimes effects a little bit higher. And in this specific case, the observed mean difference is a little bit lower than the true difference of 0.5. We found a difference of 0.35, more or less. We can see that this difference is not far away enough from 0 to be statistically significant. Regrettably, we'll find a p-value that's larger than the alpha level. But does it mean that there is no effect? No, that doesn't mean anything, because we see that observing a mean difference of 0.35 is actually very likely if the true effect size is 0.5. So we should expect to find these mean differences. And if we do, it doesn't mean that there's no true effect, just means that the effect we observed is a little bit low. If we want to make sure that these kinds of differences would also be statistically significant, we would most likely need to increase our sample size. The main take-home message here is that a non-significant p-value doesn't mean that there is no real difference. We can't conclude that there is a null effect. So it might be interesting to take a look at what you actually do. Maybe if you've written a paper, you can open your paper and take a look. Or maybe if that's a bit too confronting, maybe you want to open someone else's paper, maybe a paper you're building on or that you found very interesting in the scientific literature. Open it, search for p larger than 0.05, and then see how they interpreted this result. Did they interpret it as p larger than 0.05, therefore there is no effect? Then regrettably, they made this mistake in interpreting p-values. We'll take a look at the right thing to do in a while. Another thing you could do is think that if you have falsified your prediction, if you found an effect in the opposite direction of what you predicted, and that is definitely something that would be disconfirming your prediction, that's definitely true. Regrettably, if there is no difference, if the null is true, you wouldn't find a lot of significant effects in the opposite direction. Those would actually also be a type 1 error. You would just mainly find effects that are very close to 0. So this all is not going to work. So what can we do? Well, first realize that you can never prove an effect is exactly 0. We don't have statistical methods to prove the effect is exactly 0. Nothing is going on. But what we can do is that we statistically reject effects that are large enough to be deemed meaningful. So effects where we think, okay, what do I really care about? Effects around this size. Can I now statistically reject the presence of any effect that's large enough to matter? So this is what we'll talk about in a while, and this is one way to falsify your predictions. So what you need to do to be able to falsify a prediction is to specify what is the smallest thing that I actually care about? What is my smallest effect size of interest? So when you design a study, you have to think about this in advance. This is really a question of what is actually important in your study. What do you care about? These are deep questions, and you probably want to discuss it with some people, but it's super important to think about this. If you have a smallest effect size of interest, it's a super useful thing to have. First of all, when you design a study, you can use this smallest effect size of interest to make sure that your study has enough statistical power to actually detect an effect that you care about. When we do a power analysis, when we justify the sample size in a new study, we never really know how big is the effect that we can expect. And as a consequence, we never really know which effect size to enter in a power analysis. However, if we have a smallest effect that we would care about, we can plug that number into our power analysis and make sure that our studies are always informative, regardless of the true effect size. We just know that if there is anything we would care about, we have a very high probability of finding it. So this is useful when designing studies. It's also useful when you analyze your studies, because if you said in advance, this is what I care about, anything smaller than this, I don't care about at all, well, now we can conclude that your prediction was falsified. What falsifies your prediction is whenever you find data that is statistically smaller than the smallest thing that you would care about. It's too small to matter, the end, as good as zero. So how can we determine this? How can we determine the smallest effect size of interest? There are a couple of approaches, but let's highlight two. First is thinking about theoretical predictions. What does your theory actually predict what needs to happen? And the second is practical significance. We'll come back to that later. So as an example of a study that uses a theoretical prediction to specify the smallest effect that they would care about, there's this study from an evolutionary psychology standpoint, where researchers had the theory that during the most fertile phase of the cycle of women, the women would have a healthy red blush on their cheeks. I mean, I don't know why they predicted this, but this is a prediction from this field. There would be a healthy red blush, and this would signal to men, hey, this is probably a very good time to make babies, right? So this is the theoretical prediction. Boris and colleagues thought, let's study this in a very well-designed study. They made pictures of women every day of the month, high-resolution cameras, tracked them, determined their most fertile period, and then analyzed the data. And they found that there was indeed a statistically significant increase in redness on these pictures during the most fertile time of the month. However, they also saw that the effect of the increase in redness was so small, it was too small to see with the naked eye. Now, this is, of course, a problem for the theory, because the theory proposed that men would be able to see this, but they can't. So there was a significant increase in redness of the skin. However, it was so small that men wouldn't be able to see it. Significant result, but hypothesis falsified. So this is a nice thing of having the smallest effect that matters. Even if the effect is significant, you can say, well, nice, it's not zero, but it's also not large enough to support my theory. So that's pretty neat. Alternatively, you can think about setting the smallest effect size based on what we call practical significance. So which effects would actually matter? Which would be large enough to be worthwhile? Maybe there is a difference if I actually travel over to you and I talk to you real life, basically, in front of you. But is this effect large enough to warrant me flying all the way over, right? The costs, are they worthwhile related to the increase in education that we then see? To study these kind of things, we would need to do a cost-benefit analysis. How large should an effect be if we want to achieve a sufficient benefit that warrants the costs of some sort of intervention? So these are important things. Or reversely, maybe a small decrease in educational content is actually good enough. You're still picking up enough information if I talk to you over a webcam, and the additional cost of flying over to you would not be warranted. Right? So based on the cost-benefit analysis, we can see how much do we want students to improve, and then we can determine whether something is actually worthwhile. So I think that this setting of a smallest effect size of interest is a nice way in which statistics and theory interact. So sometimes people talk about improving the way that we do science as mainly tweaking statistics and improving that we don't p-hack anymore. So we don't mess around with our data analysis. But this, I think, is really interesting because here we see that, yeah, you actually have to think about what your theory predicts and then adjust your statistics to this. So that's a super useful thing, I think, to do. Now, if you have determined whatever you care about, then there are a couple of approaches that you can use to then actually statistically test whether you can falsify your prediction or not. The first is equivalence testing, which is what I'll explain in a bit more detail because I know most about it, but I also highlight two alternative approaches. One is estimation, which can be Bayesian estimation or just an estimation approach. And there are Bayes factors, which is also a Bayesian approach, but then a Bayesian hypothesis testing approach. So these are three different ways, and I invite you to take a look at all of these if you're interested in making sure that you design a study where you can actually falsify your predictions. What all of these approaches have in common, and what's the most important thing, is that you specify the alternative hypothesis. Remember, we typically do a no hypothesis test. So we test against zero. You don't have to think about what you're testing against. If you want to falsify a prediction, you have to specify, well, what am I actually predicting? And that's a super good thing to do. Think in advance of what would I actually expect to happen, and can I reject that I have observed something close to what I predicted? So let's have a concrete example of this. This is from a paper I wrote with Christopher Harms. In this paper, we highlight a couple of these approaches to falsifying predictions. Here, the story is, let's think of whether an 8-week meditation class can reduce lower back pain. I mean, sitting is the new smoking, people. It's very problematic. So people will get back pains, and let's see if we can help these people through some sort of meditation class, right? So we do an 8-week meditation class and then see if they feel better and have less back pain in the future, compared to a control group that has some sort of very similar intervention, but not meditation. Now, let's say that we performed this study, or here I mentioned a waiting list control condition. Okay, it's not perfect, but okay, good enough. So here we have our two groups. So here you see the individual observations. There's a group that had a meditation class. There's a group that was just on the waiting list, and we can just visually see they're more or less similar. And these are completely fake data points. We just simulated some data. There's no real difference, because if we statistically test this, then despite that we had a pretty large sample size, because, you know, they were free anyway, we just made them up, then we can see that we can't reject the null hypothesis, regrettably. We have our t-statistic, our p-value is 0.101. I mean, 0.1, because otherwise you might be tempted to change it into a directional prediction afterwards. We're not into that stuff anymore, but in this case, it wouldn't even matter. So this is not significant. Now what are we gonna do? We can't reject the null. So we have to think about how we can use something like an equivalence test to reject the presence of a meaningful effect. So for back pain, what would be a sensible smallest effect size of interest? We need to determine this, and then we specify a range of values that are within this smallest effect size of interest. So we call this a region of practical equivalence, values that are so close to zero that basically we don't really care about any effect in this range. And if we do this, then we can test whether we can reject effects outside of this. So for the 4 possible situations that we have, if we do this, so now we are combining an equivalence test with a null hypothesis test. We can reject the null hypothesis, or we can reject the presence of a meaningful effect. Now here we say that the region that we consider too close to zero to matter goes from minus 0.5 to plus 0.5. So half a scale point difference. Anything up to half a scale point difference in either direction, we consider too small of a difference to matter. So we have 4 possible outcomes here. We can see the test result, which is the square on the screen. That is the observed mean difference. And we can see the bar around it, which is a confidence interval. Now, it's useful to remember that if a confidence interval excludes certain values, then if we would test against this value, then we would be able to reject it with a statistically significant result at our alpha level. So a confidence interval sort of overlaps with a statistical test. Now let's start maybe with scenario B, because in scenario B, we see that we have our observed effect size. We have a confidence interval around it, and we see that this confidence interval doesn't overlap with 0, which is the line in the middle. So what does it mean? The confidence interval doesn't overlap with 0. It means we can statistically reject 0. Nice. So our null hypothesis test will be statistically significant. We can also think, is it actually large enough to matter? Can we reject any effect that is large enough so that we care about it? If we want to do a test against these values that we care about, we have to compare the confidence interval. Does it exclude values that are either smaller than minus 0.5 or larger than 0.5? And in the case of scenario B, we see that's not the case. The confidence interval overlaps with minus 0.5. That means that the meditation class might even have a negative influence on experienced pain. And we're interested in effects in either direction. So in this case, we can conclude we can reject the null, but we can't reject effects that are large enough to matter, so it might be big enough that we actually care about it. Okay, useful. Let's take a look at the row above, scenario A. In this case, we again have our observed effect size, the square, we have our confidence interval around it. In this case, we can't reject the null. The confidence interval overlaps with 0, but we can reject effects that are large enough to matter because the confidence interval nicely falls within our region of practical equivalence. It falls within both bounds. We can reject effects that are more extreme than what we, extreme enough so that we would care about them, large enough so they matter. So we can reject those values. This is too small to care about. There are two additional categories which are interesting. One is actually, it's very similar to the redness of the skin example that I mentioned before. So here, condition C, we have a finding where we can reject the null, but we can also reject effects large enough to matter. So we have a practically insignificant finding. It's statistically significant, but it's not large enough to matter, like the redness of the skin example. And condition D is nice because it shows a real inconclusive result. In this case, we can't reject the null, but we also can't reject effects that still matter. So in this case, our confidence interval is so wide, we don't know what will happen. We have no reason to draw any conclusion. We'll just have to collect more data in the future and learn. All right, so this is an example of 4 possible outcomes that you can have if you combine equivalence tests with null hypothesis tests. And these allow you to falsify your prediction to a certain extent. So you can set these smallest effect sizes based on practical considerations, theoretical predictions, or even sometimes based on the resources that you have. In this last case, you say, well, given what I can reliably detect with the sample size we have available, I can conclude that the effect is too small to study with the resources that we have, which can also be useful. It's not really theoretically interesting, but practically it can be useful to say, well, if we want to study this, we need much larger collaborations. So each of these ways to specify the smallest effects of interest, theoretically, practically, or based on your resources, asks a slightly different question. And it's up to you to think about, why is this question interesting? The same for setting the smallest effects of interest. What would you actually care about? That's something that you need to think about when you design your study. For the case of the back pain example that we had before, it's actually nice that medical researchers have identified the smallest effect size that they clinically care about. This is known as a minimal clinically important difference. So if the difference is smaller than this, they don't consider it worthwhile for a treatment. So then our meditation class wouldn't matter. And in this case, they measure pain on a very fancy measurement tool, namely something that's known as a visual analog scale, which is basically a line. It's a line and people just say, how much pain are you experiencing at this moment? And the minimal effect size on this measurement tool is a difference of 9 millimeters. So if the control condition and the experimental condition, the difference is smaller than 9 millimeters, then they say this doesn't really matter. So let's go back to our data that we had simulated before. Here is the plot of the data. We have the mean difference. So there is a difference between these groups, but it's not large enough to be statistically significant. We already saw this, but it is very well between the -9 and +9, which are the smallest effect sizes that are clinically relevant. So we see here the effect size is snugly between anything that would be large enough to matter. We can reject effects of 9 millimeters difference. We can reject effects that are clinically relevant. So we can act as if this meditation class has no effect whatsoever. So it's good to know we can move on and try different things. We tried it. Regrettably, we've falsified our predictions. This is not holding up. So this was a frequentist way to do this. There's also a Bayesian estimation approach. It's called the Bayesian rope test. So rope is this region of practical equivalence. Here, what you do is you calculate the posterior distribution and you compare your posterior distribution with this region of practical equivalence. It actually looks very similar to equivalence testing. Depending on the prior that you use, they might even be identical. So they overlap with a uniform prior, with a slightly informative prior. They're basically the same in practice. But here there's a Bayesian approach, and if you would have a strongly informed prior, then the results would really start to matter. And also philosophically, of course, the interpretation is different. There's also the use of a base factor approach. In this base factor approach, what you do is you specify your prior under the null and under the alternative, and then you compare both of these models and you sort of say, given the data that I've observed, how likely is one model compared to the other model, and how much should I update my belief based on the data that I've seen? And depending on the base factor, you might say, in this case, after looking at the data, my belief increases that the null hypothesis is true. There is no real effect of doing a meditation class on lower back pain. So if you apply any of these methods thoughtfully, either using frequentist or Bayesian statistics, will yield very similar inferences. My recommendation is just to use whichever of these you prefer, or if you want to, use all of them. And if they all point in the same direction, which they probably should most of the time, and we have a paper where we use both of these approaches on real data sets, and all of these cases, they point in the same direction. You can use either of these approaches what you want. I mean, people love to debate whether we should use frequentist or Bayesian approaches, but for me, I really don't care. As long as you think about what you're actually doing, then most of these approaches will point in the same direction. Now, if you start to design better studies, and this is what we're trying to do as a field, we're really raising the bar. We're making it less easy for you to sneakily find results by flexibly analyzing your data, for example, by pre-registering your hypothesis. So all these things that we do, and then we specify also what would falsify our prediction, make it increasingly likely that we will actually falsify our prediction. So Dorothy Bishop has named this Bishop's law. The better designed a study is, the more likely it is to obtain a null result. This might have something going for it. Ever since I've been improving the quality of how I do my own studies, I've definitely seen that if I'm wrong, I'm really wrong, right? I mean, I will see that I'm wrong. There's no way around it. So you have to prepare for the possibility that you'll actually find a null result. Sometimes if you study something, your prediction is not right. I mean, I personally never have this, of course. Let's be clear. When I study something, my predictions are always spot on. But I've heard that other people sometimes make a prediction and then they're actually wrong about it. So prepare for these situations. Design informative studies regardless of whether the null hypothesis is true or the alternative hypothesis is true. And nowadays, if you would design a registered report, so you perform a study which you submit for peer review, and then you ask people to review the results or the method and the approach and the theoretical ID before you have collected your data. If you follow the submission guidelines of something like a registered report, you will see that they start to ask, how can you design an informative study, both when the null hypothesis is true as when the alternative hypothesis is true. So people are starting to move towards the requirement that if you design a good study, you've designed it in a way that it can support your prediction if your prediction is correct, but also that it can falsify your prediction if the prediction is incorrect. There are also other journals that now have guidelines that prevent interpreting a p-value larger than the alpha level as the absence of an effect. You can't conclude an effect is absent based on a large p-value, so you'll have to learn other approaches to be able to say, okay, nothing is going on, or at least nothing that I find interesting, right? Again, remember, we're not really saying the effect is zero. What we're saying is this is small enough so that we don't really care about it. Now, this is important to learn. And I already mentioned before that for some weird reason, we teach our students mainly about null hypothesis significance testing. And we don't teach them about these equivalence tests or Bayes factors or Bayesian estimation approaches, even though these are all simple enough to do. Especially for simple designs, you will not have a difficulty in implementing any of these approaches. For me, it sounds like it would be very sensible that the moment that we learn or we teach you how to reject the null hypothesis, we also teach you how to reject any effect you care about, to falsify any prediction. This should go hand in hand. If we only teach people one way to work, then yeah, nothing is going to be falsified. So other people have noticed this as well. They say in the absence of a true process of replication and falsification, right? So we don't have a process in which we can actually prove things wrong. The entire discipline risks a slide towards the unfalsifiable. And this would be a big problem. We have undead theories. So that's in this paper, they mention this, undead theories, theories that won't die because we have no way to prove them wrong. And this is the problem of not specifying what would falsify your predictions in advance. So we have an entire literature where theories just don't go away. They just walk around like zombies forever, which is of course not a very desirable thing to end up with. Now, another thing that's useful to think about is that if we really want to falsify these predictions, I mean, it's fine for you to specify what you are interested in, right? You can say, well, this is my smallest effect size of interest. And to a large extent, those choices or your Bayesian prior for the alternative are all very subjective choices. It's difficult to really pinpoint what is the true thing that we want to compare our data to. There's really no right or wrong answer. So this means that we have to think about this. And for some reason we haven't, right? We haven't had a discussion among peers, among experts in the field, what would actually be big enough so that it matters? And which effect sizes would be small enough to matter? So here Klaus Fiedler suggests that to do this, what we really need to do is detach our theories from individuals. We don't have our own theory that we try to defend because, well, you won't be surprised that if I propose a theory, I actually don't want to be proven wrong, right? I mean, scientists should be very, very, let's say, moral and standing above their own data, have no sort of self-interest to say, yeah, this is what I've worked on for the last 20 years. Oh yeah, if it's all wrong, sure, I would love to know. I mean, that's a very nice attitude to have, but maybe a bit more than we can expect. But what we can expect is that I do something and then you try to falsify my findings. That's a little bit more how science works. That's a bit more what we can expect. So Fiedler says, yeah, if you want this, they have to detach these theories from individuals, make sure that many different researchers working in different labs and driven by different motives, right? This is important. So some people want to find that the thing is true, but maybe some people want to show that the fact is not true, right? So they can be driven by different motives. That's probably good. Participate in a pluralistic endeavor. So we all have our different ideas and our different viewpoints. We approach a theory from these different perspectives. And he says, only then can the full potential and the weaknesses of a theory be expected to unfold. So if we want to be wrong, we have to open up our theory so that other people can try to falsify it. And it really helps if we say, look, this is what would falsify my prediction. What we now often see is that people don't falsify their predictions, or they don't state what would falsify their predictions. And as a consequence, if I perform a replication study of the work of someone else, this person can just say, well, I guess that the effect is smaller than we thought previously. But it just keeps getting smaller and smaller and smaller, up to the point where you think, really, does this still matter? But if people never make a prediction about what they actually think matters, then they basically can get away with never being falsified. They just say, well, I guess the effect is smaller than what I predicted. So it's an undesirable situation. So it's important that whenever it's possible, whenever you can, think about and also clearly state in advance what would falsify your prediction. That's not a new thing. There are wonderful books from the 60s, among others a book, Methodology by De Groot, which is a Dutch researcher who wrote a still very relevant book about scientific methodology. And in this book, he says exactly this. Any researcher who proposes a prediction and makes a theory should also clearly specify what would falsify this prediction in advance. And if you read any scientific journal, you'll see we are relatively far removed from this state. All right, so that's all I wanted to talk about. I think I'm done a little bit early, but we have some room for questions if anybody has any questions, and thanks for your attention.
Thank you, Daniel. I've got a list of questions here. People are asking, to what extent are the ideas that you're working with new ideas versus ones that are translated from prior thinking or research in other fields like medicine, but have
Yeah.
been forgotten or ignored.
Yeah, exactly. So there's really nothing new about this thinking. What's important is that if you look at the scientific literature, many scientific literatures, at least let's say the social sciences, you see very little of this. There is very clear evidence of extreme publication bias. So everything we do works out. So people don't specify in advance what would falsify their predictions. We don't see those end up in the scientific literature. We see them end up in these registered reports. So there now we start to see that people actually make predictions and then they don't work out. So it happens, but it wasn't entering the literature. Now, statistically speaking, all of this stuff actually exists in many other literatures. It's a very good point that somebody made. It's definitely true. So there's nothing new statistically about this. The example I mentioned about equivalence testing, for example, was designed in the 70s in medicine, where they are very interested in finding new drugs that work exactly as well, but are much cheaper or easier, or new therapies that are much easier as the existing medicine. So practices such as equivalence testing or showing that a new technique is not worse, so non-inferiority testing, or it's sometimes called superiority testing, if you want to show that something works better than another example. All of these approaches exist for a very long time. They don't exist in our curriculum. So if you would open a statistics book, an introduction to a statistics book, you don't see these kind of tests to reject any effects. We teach people still only this null hypothesis test. Well, it depends where you work. You might have heard about these tests long ago. You might be using them. In my experience, when I ask people the questions that I asked earlier, like what would falsify your hypothesis, the answer is relatively rarely, well, we would perform an equivalence test. People have not heard about these things. So the main thing is education. I think we need to teach people about this. We don't need to develop these methods. I mean, yes, there are alternatives. There are more fancy approaches maybe, but the main point is that we're not introducing these in education. So this is all old stuff. And actually, many of the things that we see in the scientific reform movement, there's nothing new about these things. These things have existed for a very long time, but only now are we starting to take them seriously and actually spread the word. Like these kind of video lectures are very useful to reach many more people. So the internet makes it much easier to learn about these new techniques, even though they have existed for a very long time.
Mm-hmm. This next question deals with your response. I think it asks, where do you think you get the most leverage for spreading these ideas and standards, which seem like they'll improve science? Are they journal editorial boards, grant funders, undergraduate training?
Yeah. So I think it's difficult to, like, where do you have the most leverage? It depends on what kind of scientists you are. I mean, again, as I mentioned before, you have to be a really, really objective scientist if you want to prove yourself wrong. And by all means, be this scientist. This is very good. So if you design a study and you clearly say, okay, I would be wrong if this happens, and then you show, okay, I'm wrong, and I'm still going to try to publish this result. So unlike all these people that we saw in the beginning who don't try to publish this, perfect. So education is important, but we see that if we don't motivate people to specify these things, they typically don't. And this is why slowly at the level of journal submission, that is where you can really argue something about, hey, you should interpret things in a way so that you can actually falsify your predictions. So journal standards are good so that people don't say, okay, nothing happened, like I can reject the presence of anything going on, when in reality they can't make that distinction, right? So they can't make that conclusion. So that's one approach where you can prevent misinterpretations. But what you really need is to start when they design the study. So you need to make sure that they have these decision rules of when things are falsified when they design the study. So how can you get people at this point? Well, it turns out that these registered reports are a really excellent way to do this, because there people have designed their study, then they submit it for review. And that's the point where either in the submission guidelines or based on the reviews, you can say, hey, wait a second. You designed a study. It can only be right. When will you be wrong? Can you please specify this? Now, interestingly, when you see people try this, very often you see that it's super difficult for them to even specify when they would be wrong, right? So this is a very difficult question you're then asking people, like, hey, say when the effect would not matter. Then people start to think, they're like, I don't really know. So maybe we need to take it even one more step back, right? Not ask the individual researchers when they submit their study for a registered report, what would falsify it? Maybe we need to organize communities. And if I would have a magic wand and I could make it happen, I would say, if you work in a specific field, you study something, get expert panels together, everybody who has an opinion about this, get them together, make them discuss what would matter. We're studying this thing. How big do effects need to be before we really care? And of course, it's easy to say, well, anything would be interesting. But if anything is interesting, you have to do studies with 200,000 people or something. You know, it's very difficult to do huge studies. So there will be something where people say, no, okay, honestly, if it's smaller than this, we don't care about it. And again, there are very nice papers from the 80s where they already try this. So they get some experts together and they say, okay, for this medication, how much of an improvement should we see? But the number of papers that have tried this are very fragmented. They're very few. So for some reason, yeah, we know that we need these boundaries, but there are not a lot of fields where people have actually debated with each other, like what would be a sensible boundary. So I would guess the starting point is get experts in the field together, make them debate this, and then every researcher working in this field can either say, well, it's nice, but I disagree. I have my own thing, fine. Or they can say, this is what I will use. So that would be an interesting starting point if people in the field get together and say, all right, this is it for our research topic.
Okay, and I'm looking at one more question here, Daniel. It says, people have complained about the problems with the status quo with null hypothesis significance testing in the social sciences for decades. When do you think the tide will turn and a critical mass of people will participate in reform, or at least rethinking of standards like the ones that you're promoting?
Yeah, I mean, it's a good question. So I think you see more and more young people who are interested in these kind of things. And again, education makes it like online education, for example. You mentioned this online course. So yeah, this kind of stuff, if you want to learn about it now, you can go somewhere and you can be educated about it much easier than before. Is this enough? I'm not really sure. So you see that these reforms, they do slowly start to spread. And it's a difficult question to examine how this happens and when it happens. There is a certain group of people who just want to do the best science they can do. And this is part of it, right? They listen to these kind of talks. They're like, okay, yeah, nice. So I realize how I can improve my own research. Then maybe they have to try to convince their collaborators of this, which, you know, especially I hear this from PhD students, is not always easy. If they work with somebody who didn't do these kind of trainings and didn't learn about this, they say, I don't know what this is. I've never heard about it. Just do it like we always do it in the past, right? So you'll see these kind of effects happen. So that is difficult for individuals to start. There is the extreme alternative approach. If you take a look at what happens in medicine, which I think for many things is actually a good thing to look at for, I mean, my background is in psychology, right? So it depends on what you work in as a field, but for us, medicine is definitely quite ahead in many things and we can learn a lot from them. In medicine, for randomized controlled trials, you have the FDA who has just really strict top-down rules about what has to happen. So that is an alternative approach, right? And the question is, what needs to happen before these top-down rules get instigated? Now, of course, in medicine, you know, if you do a bad job, you're literally killing people. So, but the alternative question is very simple. Like, well, does your research actually matter? You know, I mean, what are you studying and does it also have negative consequences? Maybe you're a clinical psychologist. You work on new kind of therapies. Well, that's pretty severe, right? I mean, if you think you're helping somebody, but you're not, that can have major consequences, maybe more than a drug that has some bad consequences. I mean, not every drug kills people, but bad therapy might, you know, keep people depressed. So whatever kind of topic you study, it can be either something that is very wasteful when implemented or those kind of things. Your research might also have real consequences. That the question is, how long can we just do our thing? And honestly, these kind of practices, like misinterpreting a p-value that's not significant as the absence of effect, is so common. How long will we accept these kind of misconceptions before somebody steps in and says, okay, now it's done? Now, we don't have an FDA in many other fields, so we are not really at a risk of doing this. But you see that, for example, when it comes to sample sizes, so I'm taking the question a little bit broader, right? Not just about this specific thing about falsifying, but for example, sample size justifications. you can clearly see that some fields are now starting to implement power analysis or sample size justifications, and funders in these fields are starting to request these kind of numbers. Again, it's just one starting point, but it's at least a place where there are external parties that force researchers to do certain things. Is this likely to happen quickly? I don't know. I think there is a decent number of people who have a sort of bottom-up approach. Specifically for the case for falsification, there's one other way in which it spreads, which is kind of funny. And that's, I think, I'm not really sure, but I've heard it so far. I mean, most of the emails I get from people are not, hey, I learned about this, I want to do it, but they originate from a different viewpoint. And that is, I submitted my paper and an annoying reviewer told me to do this. So this seems to be nowadays the most common way in which something like specifying what would falsify your prediction spreads, and that preventing this p-value larger than an alpha level means no effect. This misconception is stopped by smart reviewers who say, I got you, you have to fix this. And then, that seems to happen a lot because I get a lot of emails where people say, well, a reviewer asked me to do something with this. So that is definitely one way in which, as a reviewer, you can make a very valid point. You can prevent a misconception. And that seems to happen a lot. I'm not sure how often these reviewers themselves already design a study and specify all this. Maybe they also need to wait for a reviewer to tell them, hey, you've made the same mistake. But on the level of reviewers, people have some leeway to point out problematic inferences and ask people to do it. Now, it's important that if a reviewer asks you to say what would falsify your hypothesis, you've already collected the data. It's not an ideal process anymore, because preferably you would specify all of this from the starting point, again, in a registered report. But nevertheless, at least you can prevent the misinterpretation of a non-significant p-value after the fact. And it is always interesting, even if after looking at the data, people ask you, well, what would falsify your prediction? You have already looked at the data, so it's not perfect, but you can still say, let's think about this question. And you can put it somewhere, make some informed decision about it and say, well, this seems a sensible approach or not. And this would at least get the discussion started in a field, right? Because if a lot of people do this and there are these values out there, other people can say, I don't think this value makes sense. Why not? And having this discussion, again, in any way that it starts, either through experts discussing this, as you see sometimes in some research fields, or people who are just working on this, I don't know, talking about it on Twitter, saying, hey, what are you doing? What should we do here? Have the discussion. That is the real important thing. And if a reviewer starts the discussion for you, then so be it. Don't be too annoyed by them. They're trying to do a good thing.
Okay, cool. Daniel, before we wrap up, is there any way that you would advise people if they wanted to learn more about what you were doing or similar types of ideas, like where they could find out more?
So I think, you mentioned this online course. I don't want to advertise it too much, but I mean, just to be clear, it's completely free, right? I'm not making any money here. You can just enroll for free. You can do this. There are more and more good papers about this. There's a journal in general, if you want to learn about these kind of things. Psychologists have started this journal, Advances in Methods and Practices in Psychological Science. There is a whole special issue in Advances on Methods and Practices in Psychological Science on null results. What are you supposed to do with null results? And we have a paper in there about equivalence testing. There is a paper just on the philosophy of falsification. Why do we want to do this? Super interesting paper by Fiona Fiedler and colleagues. There are papers using alternative approaches like Bayesian approaches and those kind of things. So if you can find this special issue from 2018, I think that's a very good starting point to learn more about it. You can browse through, learn a little bit about why to do this. So that's a very good starting point. I also think that it would be fun if you have a lab meeting, for example. Just throw this in the group. Just get the discussion started, because you are an expert on your research topic, right? So people who write papers about the statistics, but that's the boring part. Again, we have figured most of that out for many years. The real interesting discussion is, what matters? What do we find interesting? And you are basically already the expert about this. So if you want to figure that out, that's the most important, challenging part. Start a discussion in your lab group about these topics. Like, what do you really care about? And why is something too small to matter? I think that's a good place to start, actually.
Cool. Well, thank you very much, Daniel, for such a cool presentation, and thanks to everybody else for attending. We hope you'll come back next Friday at the same time for Scott Long's talk on a computing workflow for reproducible results. That's it for us. Hope to see you next Friday.